Come on in. How's it going, John?
Hey, I'm doing good, Professor Younger. How are you?
Not bad.
Yeah. Awesome.
Feel free to ask any questions. We got about 4 minutes before people come online, but I want to make sure I got here on time. Sometimes the internet just gets slow getting up here, so I can start at like 8 till time for class to start, and it doesn't necessarily turn on by then. So sometimes they even turn it on earlier.
Gotcha.
I just took chapter 18 homework and it was due 9/4. I went ahead and made the homework part due on 9/6, and the conceptual is still due on 9/4. Also, of course, the intro to MATLAB and mastering and the physics primer are both due on 9/4. Yeah.
Professor Younger,
Yes.
is it required to do the intro to I think it's like intro to mastering physics or whatever if we did it last semester? Because
No, it's extra credit. The same thing with the physics primer. If you hadn't done it, I would recommend doing it, but if you have done it, I wouldn't waste my time.
oh, okay, so it's extra credits. Like,
Yeah.
so does that mean it
Yeah, so
covers
like
like
I
the
told
homework or
everybody, I'm
whatever?
dropping two lowest homework grades. I'm actually dropping four because those are in there.
Oh, okay, sweet. All right, thank you.
You're welcome. Anybody else? Got more people coming in? That's good. Anybody else have any questions? Your towels here are coming in. I got my Carolina blue on today because one of my homes is in mourning.
Professor, so the physics primer, that's a homework assignment, right? But is the other one
No, both of those are extra credit. The physics
other extra
primer
credit?
and the intro.
Okay.
No
Because I
problem.
was looking at them, the physics primer says that the things are worth points, and the other one says that they're practice. I was
They're all
confused.
supposed to be worth points. I don't know. I must have grabbed the wrong intro, but I count them as extra credit either way. So
Okay. Thank you.
you're welcome. Anybody else have any questions? It's almost time for class to start actually, but now's the time you can ask. I'm always going to try to start off, by the way, folks, with a question session. So if I just jump in and start talking about stuff and you have questions, make sure you stop me. I don't mind, and in fact I appreciate it. My goal is to always start class with taking questions. If they get too cumbersome or too much or take much time, I'll say hold it for afterwards, and we can either do it immediately after class before you go to lab on Tuesdays or immediately after class on Thursdays. But the main thing is we'll get it done, or we could even make a personal Zoom meeting where we can address it there. I can even film it so that way we could put it online so people could get the answers to the question even if they didn't have it themselves. So, all right. Well, it looks like we got 7 of you. That's actually, there's not that many people in the class. I think there's only 9 if I remember correctly. So we're pretty close for this class. So I guess we'll go ahead and get started. If no one has any questions, the chat is up in case you do have any. So let's go ahead and get started. We're going into chapter 18 now, and believe it or not, I do a very short version of chapter 18. I want to tell you, for instance, that chapter 18 is called Kinetic Theory of Gases, and kinetic theory is like the initial part of what we call statistical mechanics. Statistical thermodynamics is another name for that course, but I really like calling it statistical mechanics because thermodynamics was my least favorite science class, and statistics was my least favorite math class. So statistical thermodynamics just sounds horrible. So to me, I always call it stat mac or statistical mechanics. But kinetic theory is sort of predecessor to that. You're using the ideas of the atoms or molecules being in motion to predict the macroscopic behavior of things, so like collections of gases and stuff like that. And that's what I'm going to do. And this derivation I'm getting ready to do, you can sort of think of it as a one way of thinking of it would be like using these rules that we're arbitrarily applying to molecules, which can be read as atoms as well. Using these rules, we're going to end up coming up with the ideal gas law. What I like to think of it as is we end up getting something equivalent to part of the ideal gas law that allows us to determine the relationship between temperature and translational kinetic energy. So that's probably a more realistic or more correct way to say it, but both of them are in some sense true. So I'm going to start off with sharing my screen, specifically the screen for the textbook. So let me do that real quick. So these are the conditions that we're going to use. It says the ideal gas law and the molecular interpretation of temperature. So what I'm ultimately going to get is a relationship that shows us that if we sort of could stop time and then survey all the molecules in my body, say at that instant, and quickly ask it, hey, molecule number 1, what's your mass and what's your average translational speed? And then we calculate kinetic energy for that, and then we write it down, and then we go, all right, molecule 2, do the same thing, and keep doing that until we've attacked all the molecules and or atoms. What I mean is atoms that are loose, not in molecular bonds. We would address those as well. But when we're all done with that, we could then, in some sense, take an average of all those and just multiply it by a number, and boom, that number would produce the temperature of our body in Kelvin. So in that sense, temperature is defined to be the average random kinetic energy of translational motion of the atoms or molecules in an object. So we're going to do with that, but we're going to make some assumptions, and the assumptions representing the basic postulates of kinetic theory are the following. First off, I think I can make this screen a little bigger. It did. Okay. Kill that. It says, number 1, there are a large number of molecules, capital N, each of mass, lowercase m, moving in random directions with a variety of speeds. This assumption agrees with our observation that gas fills its container, and in the case of air on Earth, is kept from escaping only by the force of gravity. 2, molecules are, on average, far apart from one another. That is, their average separation is much greater than the diameter of each molecule. 3, the molecules are assumed to obey the laws of classical mechanics and are assumed to interact with one another only when they collide. Although molecules actually exert weak attractive forces on each other between collisions, the potential energy associated with these forces is small compared to the kinetic energy. Can't stop yawning. I even took a nap to keep from doing that, but anyways, it didn't happen. Collisions with another molecule or the wall of the vessel are assumed to be perfectly elastic, like the collisions of perfectly elastic billiard balls. We assume that the collisions are a very short duration compared to the time between collisions. Then we can ignore potential energy associated with collisions in comparison to the kinetic energy between collisions. Okay, so those are the various premises we're going on, and now I'm going to derive a relationship for the pressure. In other words, I'm going to try to calculate the pressure on the wall of a container due to the translational motion of the atoms, or in this case, the molecules as well, because we're treating everything as if it's a molecule, and there's no loss of generality because, in fact, if we just treated them as atoms, there would be a loss of generality because there's some cases where the atoms combine with other atoms to make molecules. So in this case, we're making molecules, and of course, the simplifying version would be that the molecule is an actual atom. So now I'm going to go with this. Oops, I might want to start on the proper page and the proper notebook for that matter. Okay. All right. So let me do another share screen. This time it's going to be with my iPad. And what I'm going to do is hopefully get this to actually share correctly. Looks like it's working. Okay, it might take a couple seconds. What I'm going to do is imagine a coordinate system. And in this coordinate system will be an x-axis, a y-axis, and a z-axis. Not that necessary, to be honest with you, but I just wanted to fix it in space. So now I'm going to take a container, and the container is going to be well, I'll draw it like it's a perfect cube. It doesn't necessarily have to be, but it will be very close to one. Okay, and I'm going to assume a couple things. So these parts that I'm drawing dashed are the parts that are technically behind the face that we're seeing. As you can tell, I got a little off because I drew the y-axis at a different angle than I drew the edge of the cube. So what I am going to say is that this distance right here is L. And if it was a perfect cube, then the other two dimensions would be L as well. But we're not going that specific. We're just going to say that this face has a surface area A, and this face has a surface area A. And when I say that first one, that's the face that's in the YZ plane, okay? Now I'm going to imagine a molecule in motion, say right here. That was not supposed to be that. I'm going to imagine a molecule in motion right here, and this molecule is headed to run into the wall. Now, let me zoom in on that for a second so you understand what I'm saying. That molecule has a velocity that looks like this. What that velocity is a velocity component in the x direction, a velocity component in the y direction. Got more people coming in, hold on. And a velocity component in the z direction. So that's the total velocity would be vx plus vx I hat plus vy j hat plus vz k hat. But I'm focusing right now on just the x hat component, because what we're thinking about is when this molecule collides with other molecules, or specifically in this case, I'm talking about it with it colliding on that left wall, because that's the wall on which I wish to calculate the pressure. When it does that, what's going to happen is conservation of kinetic energy is going to make it move up and to the left and back into the screen a little bit, bounce off that wall, and then it's going to come out with the Vx component of velocity just reversed. So it's going to go from Vx in the negative direction to Vx in the positive direction with exactly the same magnitudes. That's just what a kinetic, or excuse me, an elastic collision conserving kinetic energy is going to cause. And of course, then it's going to bounce back and move with a velocity Vx to the right. It's still moving in the Y direction. It's still moving in the Z direction. And in fact, it might be close enough, for instance, to the back face to bounce off that once, but that doesn't matter because the only thing that's going to change is the Y velocity is going to change from, in the first case that I have drawn, a positive Vy, and then after the collision will be a negative Vy. It might collide with the roof of the block as well, or of the box as well. But again, the VZ is just going to go from a positive VZ to a negative VZ. So it's constantly just going to move. Like if we had something that could follow the shadow just along the x-axis, we would see the x-axis has a little shadow on it, and it's moving with a velocity Vx, 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 bounces off the wall, Vx, 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 bounces off the wall, Vx, Vx, Vx. So the magnitude is always going to be Vx. It's going to change directions as it bounces, but it is going to always have a magnitude of Vx, okay? So that's sort of the picture that we're going with right here, is that we're doing that. Now, what we know is that pressure is force divided by area. Now, why does it keep doing that? I keep trying to write it in a different color, and I forget to actually, I changed the color, but I don't actually select it, so that's my fault. Damn it, if I did it again, that was sort of right, just the wrong color blue. That is not the blue I wanted. That's the blue I wanted. Okay, so pressure, P, is equal to the force divided by the area. And normally we specify the area perpendicular to the force. So in this case, we're talking about a force that's actually perpendicular to the area. But the main thing is now we can use Newton's second law, and we can say the force is equal to delta P over delta T. Now that's what it would really be. In our case, we're just coming down to the x part. So F sub x is going to be delta P sub x over delta T. And again, the delta is sort of a limiting thing. And ideally what we want to do is take a limit as delta T approaches 0. But we don't actually physically have to do that because we're actually examining molecules that are going so fast that if you're actually using a regular sized container, you will know that it's going to collide a bunch of times. In other words, a regular size, not one comparable to the size of the Earth or something like that. So here is the derivation. So what I know is initially from my drawing, the momentum in the x direction is saying this molecule has a mass m, is in fact F is equal to m times negative Vx, because that's the, oh, actually, no, I got to do it the other way. Sorry about that. Hold on a second. It's delta P is final minus initial. The final is that it's going to bounce off and then be coming out this way. So at that point, the velocity is going in the positive x direction. So I'm going to say it's positive mvx minus negative mvx over delta t. So that gives me 2mvx over delta t. That would be the force due to that one molecule hitting that one left wall. Okay. Now, what I would like to know is how long in time goes on between hitting that wall, going off, doing its thing, and then hitting that wall again. So as I told you, if we followed the shadow, and I'm imagining like the sun is directly overhead or something, and it's casting a shadow of this molecule on the x-axis, the molecule is going to be moving to the right with a velocity v sub x, and then it's going to bounce off the right wall. It may have bounced off the top wall, the back wall, the front wall, the bottom wall as well, but that doesn't matter. It's not going to slow it down. It's going to then bounce off the right wall and then move to the left with a velocity Vx, or with a magnitude of velocity Vx, and then it's going to bounce off the left wall, and so on and so forth. So what we can figure out is that delta T is going to be distance divided by the velocity. Well, the distance it travels between hitting the left wall and hitting the left wall again is 2L, and the velocity that it's traveling at is v sub x. So I'm just using velocity equals distance divided by time to solve for time, and you see time would be distance divided by velocity. So now I can put that in there like this. And when I do that, I'm going to get equals 2mv sub x over 2L over v sub x, which equals, notice the 2's cancel out. Now I've got mv sub x squared over L. Okay. Now that happens to be the force occurring on the left face due to that one molecule. Now, in reality, there's N molecules. So there are actually N molecules colliding with the left face. And the N is so large that it's basically going to be at every instant of time, there's going to be a plethora of molecules bouncing off that left face. And that left face will therefore feel a continuous pressure. Even though it's discrete collisions, there's so many of them, it'll be literally tens of millions of them, probably even a larger number than that, hitting at any one instant and every other one instant, okay? So now what we're going to do is try to find the total force due to all the molecules. So F due to all N molecules. Now, remember, all these N molecules will actually have different V sub X's, right? There's a whole litany, a range of velocities down as low as 0 and up as high as, several hundred meters per second, stuff like that. So the total now is F is equal to M over L times V sub X 1 squared plus V sub X 2 squared plus ... plus V sub X N squared. That turns out to be the total force due to all those individual velocities and individual molecules. Does that make sense to everyone? Anybody have any questions on that? So if we'd like to, we could sort of try to represent this with an average. So let's represent the force with an average V sub X bar squared. So what we're considering here is there's a strong likelihood that for each molecule you find moving to the right at, let's say, 50 meters per second, you're going to find another one moving to the left at 50 meters per second. So if you took the actual velocity and average that, there's a good probability that that would be 0. In fact, there's very specific cases where that is exactly 0. There might even be a scenario in which it's always 0, but I'm a little lost in thinking about that right now just because it just hit me. But anyways, what we're going to do is we're going to avoid that possibility by calculating the average of the squares. So it turns out that the average of the square velocity, V sub X bar squared, is equal to Vx I should write that the same way I wrote it before. That's v sub x 1 squared plus v sub x 2 squared plus dot 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 plus v sub x n squared. So we would imagine taking the instantaneous v sub x for each of the individual molecules and squaring it, and then adding them all up and dividing them by n, and that would actually give us the average. With that in mind, then we can see that sum v sub x 1 squared plus v sub x 2 squared plus dot 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 is actually equal to n times v sub x bar squared. So we can now replace that whole parenthetical here with n times v sub x bar squared. So let's do that. I'll do that on the next page. We now have f is equal to m over L times n v sub x bar squared. Now that's the total force on that left wall, but it's not really in terms of anything that's useful. It's in terms of the, random average square velocity in the x direction. But we can get it in terms of the average random translational velocity by recognizing this. So there's something called the equipetition theorem that we occasionally use in physics, specifically in statistical mechanics, statistical thermodynamics, that sort of stuff, kinetic theory. But it basically says, hey, in a physical system, you have so many molecules and atoms, on the order of Avogadro's number or larger, 10 to the 22, 10 to the 23, that kind of thing. If you give it, if you say each of those atoms or molecules has 3 ways of taking in energy, and you apply 3 million joules to the system, then each one will by default get exactly 1 million joules. In other words, the 3 ways will divide up evenly. If there was 10 ways, then each one would get 1/10. And if there's 142 ways, then each one would get 142th of the different amounts. So the main thing is what we know is that v sub x bar squared is in fact equal to v sub y bar squared, which is equal to v sub z bar squared. Because in reality, if you're talking about just translational kinetic energy, there's only 3 dimensions for it to go in. There's the left-right, which we could represent by x. There's the in-out, which we could represent by y. And then there's the up-down, which we could represent by z. And that being 3 different tranches of energy sinks, if you will, then each one will get the exact same amount of energy. And if you talk about kinetic energy is 1/2 m vx squared plus vy squared plus vz squared, with the v's in parentheses. So it's 1/2 m parenthesis vx squared plus vy squared plus vz squared. So by doing that, and then realizing that v squared is equal to vx squared plus vy squared plus vz squared, you then realize that vx squared is equal to 1/3 of v squared. Because, vx squared, vy squared, and vz squared could be written as 3vx squared, like that. So now that we have that, we can go ahead and replace the v sub x squared with 1/3 v squared with a bar over it, because now we're talking about means again. And in fact, I could have put a bar over top of all of them. That's what the bar over top of it means. It just means an average. Sometimes they'll put it in less than, greater than symbols. Other times they'll put bars over it. We're using it as bars. So what I ultimately am going to do is I'm now going to say that the force is equal to m over L times n times V bar squared over 3. Now that looks pretty good. And in fact, it is pretty helpful. I can convert that to kinetic energy that we know of. In other words, the kinetic energy of Newton, not the kinetic energy of Einstein. And when I do that, all I have to do is take the 1/3 and put that out front, put the N over L here. I left the numerator blank on purpose. And then I'm going to write here 1/2 mv bar squared. Now, I just made that 1/2 up out of thin air. I'm not allowed to just do that. I can't just multiply an expression by 1/2 and get away with it because I've changed the expression. But if I simultaneously multiply by 1/2 and 2, then I can, and that's why I left the numerator the way it is. So what you see now is this quantity right here is in some sense the average kinetic energy, which we often write as KE. I'll tell you, some books will write it as a T, and that, in which case it'd be a T over it, but I'm going to use it here as just plain K with a bar over it. Okay. So we now have the force acting on that wall, the total force acting on that wall, being related to the average kinetic energy in some sense. It's the average kinetic energy in the sense that we're using the what we call the root mean square velocity. So if you were to take the average or the mean of the square of the velocity, that would be the mean square of the velocity. Now, if you take the square root of that, then you'd be taking the root mean square of the velocity, which is like a representation of V. Okay. So that's also called VRMS, but now we're in a good spot. We can actually relate this to pressure, because pressure is force divided by area. And remember, we said the area of that left-hand wall was A. So now what I'm going to do is I'm going to say 2N over 3 A times L times average kinetic energy. Just like that. Can anybody tell me what A times L is for that whole box? Here's the drawing in case you forgot. Anybody? Feel free to do it in the chat. Let me make sure I've got my chats visible. Yes, I do have them. Yes, it's area times length. And the area times length is there's another word for that.
Volume?
Volume, exactly. So now what we have is 2/3 N over V, volume. I'll put a capital V so we don't mistake it with velocity, times average kinetic energy, or specifically PV is equal to 2/3 N times the average kinetic energy. But we already knew, for instance, PV is equal to nRT. And we also knew that PV is equal to N times Boltzmann constant times T. That's the one that's helpful for us. So if I now take those two relationships and this relationship, okay, what I will get is basically 2/3 N times the average kinetic energy is equal to N times the Boltzmann constant times T. You can see that clearly the capital N is going to cancel out. And in fact, the average kinetic energy makes it. The average kinetic energy, which we're defining in this specific case as 1/2 mv squared bar, which equals 1/2 m VRMS squared. that's going to be equal to 3/2 kT, where K is equal to the Boltzmann constant. Actually, Boltzmann's constant, which equals 1.3807 times 10 to the negative 23rd joules per Kelvin. Okay. So this is the big.
What is the RMS?
That's RMS for root mean square. Is that the one you're talking about? This little subscript on the V?
Yes.
Yeah, that's RMS for root mean square. It's the same one like when you maybe tell someone that your receptacle is 125 or 120 volts. That's a root mean square as well. Same thing when you say your voltage is 240 or 250 or something like that. That's a root mean square as well. It just means take the average of the square and then take the square root of that. So any questions on that? See how it's sort of like a derivation of the ideal gas law? So I could have taken, for instance, the kinetic energy as being 3/2 kT and converted the PV into NKT, which is a form of the ideal gas law, in which case you treat it as an ideal gas law derivation. Or like I really did, I ended up getting PV and then compared it to the ideal gas law, specifically PV equals NKT. And that gave me an expression for the average kinetic energy of the molecules in a gas. And that average kinetic energy is 3/2 kT. So what you'd like to do is be able to use this. So let's first off think about what's the average translational kinetic energy of molecules in an ideal gas. So this will be an example. So example, what is the average translational? That's important that you know that word, okay? Or specifically that you know that word is in here. Translational kinetic energy of the molecules in an ideal gas at 30 degrees Celsius and at 40 degrees Celsius. So that's a question. Solution. K average is equal to 3/2 kT. So for part A, K average at 30 is equal to 3/2 times 1.3807 times 10 to the negative 23rd joules per Kelvin. There's really no reason to have 5 sig figs there. 3 would have been fine. 3 is normally a nice happy number for us to use. It's just stuck in my head from where I memorized it a long time ago. So in the case of 30 degrees Celsius, remember 0 Celsius is 273.15. Again, I really don't need 5 sig figs, but I'm going to write them down here just as a reminder. So in this case, I'm going to add 30 to 273. That's 303.15 Kelvin. And when I do this calculation, I will go ahead and drop the 4th and 5th sig fig and just use, well, I'll first put the all 5 and then I'll reduce it to 3 and leave it at that. So I'm going to say 1.5 times, because that's what 3/2 is, 1.5 times 1.3807 e to the negative 23rd times 303.15, and that gives me 6.2784 times 10 to the negative 21 joules. Okay. Now that also rounds to approximately 6.28 times 10 to the negative 21 joules. That's at 30.0 degrees Celsius. Okay. So that's one answer. Now, to give you some perspective what that's like, if you divided this by, let's say, Avogadro's number, then it would give you an idea of how much a mole, if you had a mole of these things, how much kinetic energy each one would have, basically. So you could do that, divide it by 6.02 times 10 to the 23rd. You could also do it for the other part. That's a helpful thing. What you'll see is these speeds are very fast. Like, it's very common for these speeds to greatly, greatly exceed the speed of sound. Actually, I'm going to fix this. This is aggravating me. So it's very common for these molecular speeds to exceed the speed of sound. So don't flip out if you get a velocity like 500 meters per second or something. That's actually probably the case. Okay. So there's that. Let's go ahead and do part B. I'll let you divide by Avogadro's number. Actually, your book does one just like it, but your book works for 37 degrees Celsius. So you can check that if you want. Then they do the derivation where they actually say, okay, oh, by the way, this is, I said divide. I didn't mean divide. But this is the kinetic energy that each individual molecule has. So if you multiply that by Avogadro's number, then you'll see the total amount of energy stored in the gas, which is what I was trying to say, but I think I said it completely wrong. Anyways, here's part B. Part B is the kinetic energy for 40 degrees Celsius. Now, I told you guys, or I might have mentioned it at least, one of the mnemonics I gave some students at Blackwater when I was teaching them matriculation. So basically switching over to the metric system, we called it matriculation. But anyways, when we did that, one of the things they had to learn was not only meters and centimeters and micrometers and all that stuff, but they also had to use temperatures. And I found this nice little mnemonic. It said 30 is hot, 20 is nice, 10 is cold, 0 is ice. So that's a really, really good way of looking at it. 30 is hot, 20 is nice, 10 is cold, 0 is ice. And if you just look at that, we're going up by 10 degrees Celsius each time, which is equivalent to going up by 18 degrees Fahrenheit each time. So yes, the 0 is 32 degrees Fahrenheit, which is also 0 degrees Celsius. If we go up by 10, that's 10 degrees Celsius. If you add 18 to 32, you're at 50. 50 is pretty cold for most people. It's good marathon running weather, but it's still pretty cold. Now, if you go up another 10, you go from 50 to 68 on the Fahrenheit scale. So yeah, that's like Shangri-La for a fat dude like me. If the house is set at 68, I'm sleeping really, really good. That's for 20. Now, if you kick up again another 10 Celsius where you're up to 30, then you add another 18 to the 68. That'll be 78 plus 8 would be 86. 86 is nasty, especially for a fat dude like me. And you can imagine I'm actually doing 40 here. So that would be, instead of 86, that'd be another 18 above it, which would be basically 104. So yeah, 104 would be miserable. And that's what we're calculating now. So 104 Fahrenheit is going to give a kinetic energy about equal to 3/2 times 1.3807 times 10 to the negative 23 joules per Kelvin times, now we're doing 40. So instead of 303, it's going to be 313.15 Kelvin. And what we're going to do is, actually, I'm going to be really easy and just divide this by 303.15 and then multiply it by 313.15. And my answer is 6.4 0.4855 times 10 to the negative 21. That should be joules. I tried to make it like it was going to be a numerator, so I made it too small. So K40 is approximately 6.49 times 10 to the negative 21 joules. And that's our second answer. So 1 mole of gas at 40.0 degrees Celsius, which is, like I said, 104 degrees Fahrenheit, has a total translational kinetic energy of that would be, in fact, times 6.022 e to the 23rd. That's about 3,900 joules. Okay. So if you threw, in some sense, a mole of gas at someone with the same kinetic energy that the total mole of gas has, then it would basically have an energy of 3,900 joules, which if you tried to say, let's consider a 1 kilogram object and how much velocity that would have, all I'd have to do is multiply the 3,905 times 2 and then divide it by 1 kilogram and then take the square root. And that would give me essentially 88.4 meters per second. So a 1 kilogram mass moving at 90 meters per second would be what we're looking at. And remember, a meter per second is on the order of 2.2, I think, or 2.2, 2.5. If you multiply that meters per second by 2.2, 2.5, something like that, that gives you miles per hour. So yeah, that's pretty darn fast. Any questions about that? All right. Let's say that. Okay, so let's look at another example. What I want to do now is I want to consider air, because air is obviously somewhat important to us. And one of the rules we use in astrophysics, or specifically planetary astronomy, one of the rules we use, or rules of thumb we use, is we often calculate the average translational kinetic energy of each of the various molecules that we know are in a atmosphere of a moon or a planet or something like that. When we find, for instance, an extraterrestrial planet, or if we just are thinking about Mars or Jupiter or well, not Saturn, Uranus, Neptune, or Pluto, or Jupiter. Those, well, with the exception of Pluto, those are gas giants. So they actually don't physically have a solid surface. They sort of transition slowly into from nothing but like atmosphere with some goo under you to slowly becoming atmosphere that crushes you to death, but maybe crushes your feet if you're right side up a little bit worse. Okay, so those outer planets aren't that helpful. But if you try to imagine an atmosphere being on Mars, or an atmosphere being on Venus or Mercury or the moon, we know roughly what the surface temperature of those planets are, how much they fluctuate. If there was an atmosphere above it, we could set up some equilibrium condition where we'd figure out what the molecular temperature of the atmosphere is. And then what you find is if the translational speed of the individual molecule is 1/6 of the escape velocity of the planet or the moon, then that molecule, that element, that compound that's in the atmosphere is transitory. It's basically going to disappear because over time it will escape from the planet. So let's look, for instance, for our Earth, and let's imagine 20 degrees Celsius and figure out what the average translational velocities of the nitrogen and oxygen are. So example here, what are the RMS speeds of O2 and N2 at 20.0 degrees Celsius. So that's our problem. Let's do our solution. Hopefully you guys are trying to think about how you'll work the solution as I'm writing it out, as I'm saying stuff, because that's the interaction you're supposed to play when you're reading your textbook, as well as when your instructor's doing their work. You want to sort of predict what I'm going to do and then make corrections as you hear me do something different. So I know, at least when I was in my classes, I'd often go off doing the calculation. You don't want to go that far, but I would often go off and start doing the calculation on my own, only to realize that I'd made some dumb mistake, like I literally didn't understand a concept or something like that. And then I had to regroup and look back. So you still want to stay engaged with the instructor, but if you're doing it with reading, it's a lot easier to do and you don't get lost. And you know, it's not like you're can't go back to where you were reading, whereas you can't turn back time with your instructor teaching. Here we sort of can because we have a video. So anyways, just try to play that game back and forth while you're trying to read your book. It'll make your reading a lot less likely to put you to sleep and more fruitful. So let's do this. We're going to say that the average kinetic energy, K bar, is equal to 1/2 mv/rms squared, but that's equal to 3/2 kT. So if we wish to solve this for RMS, we can immediately see that the 2's cancel out and we get VRMS is going to be equal to 3 kT over M with a square root. So what we'll start off with is we need to know the mass of the oxygen molecule and we need to know the mass of the nitrogen molecule. So I'm going to say M of O2 happens to be equal to, if you look, it's 15.9994. I'm going to call that 16. And then it's O2, so I'm going to call that 32. And 2 sig figs is more than enough. And that's 32 atomic mass units. So that's going to be times 1.6605. Again, I used 5 sig figs. I only needed 3. That would be more than enough. Times 10 to the negative 27 kilograms per U. So this ultimately gives me 32 times 1.6605 e to the negative. I really can't help myself at this point. That's 5.31 times 10 to the negative 26. Kilograms. So that's our mass for O2 molecules. Our mass for N2 molecules. If you look, carbon nitrogen is it's 14 it's like 14.99 or something like that. So you might as well just, or now it's like 13.99 or 14.01, something like that. It's 14 basically. So when I do N2, it's going to be roughly 28. So I'll say 28U times 1.66. There I go again. Times 10 to the negative 27 kilograms per U. When I carry out that math, I'm going to say 28 times. This gives me about 4.65 times 10 to the negative 26th again, kilograms. So now I can do part A, the root mean square of O2 at 20 is going to be 3 times 1.38 times 10 to the negative 23rd. Look at me. I only use 3 joules per Kelvin times 293 Kelvin. Again, I did it right. Yay for me. And now I'm going to divide all that by 5.31, which, by the way, is 1 sig fig more than I'm supposed to be using anyways. So 5.31 times 10 to the negative 26 kilograms. I take the square root of all that stuff, and that will give me the root mean square velocity. So I'm going to say 3 times 1.38 e to the negative 23 times 293. Now I'm going to divide that by 5.31 e to the negative 26. And that gives me 2.28 times 10 to the 5th. And if you check the units, you'll see that comes out in meters squared per second squared under the square root, because the joule is a kilogram times a meter squared divided by a second squared. Notice it's being divided by kilograms in the denominator, so that leaves meters squared per second squared per Kelvin, but that Kelvin's being multiplied by the 293 Kelvin in the numerator, so the Kelvin drops out, and I just get meters squared per second squared. So now all I have to do is take a square root of that, and it'll actually give me the right number in the right units as 478. I actually got 477.95, blah, blah, blah. So this is 478 meters per second. Remember, the speed of sound is around 330 meters per second, something like that. This is obviously way faster. And that one was for O2. So I'm going to say equals VRMS for O2 at 20 degrees Celsius. And I'm going to circle it in red or box it in red so we all know what's going on. Anybody have any questions on that part? Now, technically, I was supposed to use 2 sig figs because I only put 32 and 28 in, so they only had 2 sig figs. So if I really wanted to be strict, I would go ahead and underline this 8. And you'd see this is actually the same example that your book did. And I'm looking at your book right now. Yeah, and they rounded it to 480 meters per second, which is completely consistent with what I did. Now we're going to do the root mean square velocity for nitrogen. So VRMS for N2 at 20. That's going to be, again, the square root of 3 times 1.38 times 10 to the negative 23rd joules per Kelvin. That Kelvin down there is going to cancel out with the Kelvin up here. And that'll leave me with just joules. And as I said, a joule is a kilogram meter squared per second squared. But down in the bottom, we're going to have 20. Well, actually, I don't even have to do the 28 because I already worked that out. We're going to have 4.65 times 10 to the negative 26 kilograms down here. So that gets rid of the kilograms that occurred in the joules. Remember, joules is kilogram meter squared per second squared. What I can do is I can just take and multiply this 477.95. I'm going to multiply it by the square root of, this is crazy, but it's an easier way to do it. I'm going to multiply it by the square root of 5.31 divided by 4.65, because that's the difference in the what we call the mantissa portion of the scientific notation. So I use 5.31 for oxygen. So if I multiply by 5.31, that'll cancel that out. And then if I divide by 4.65, that'll replace it down in the bottom. And it has to be under the square root because it was under the square root before. When I do that, I get 510.7. So that's 511 meters per second. Again, I'm carrying 1 extra sig fig than I should. So I'm going to say this is 511 meters per second, which equals VRMS for N2 at 20.0 degrees Celsius. Any questions on that? Now, if you wanted to see how this stacked up, what you realize is the escape velocity is the velocity at which an object leaving the surface of a planet can actually reach infinity and just come to zero velocity. So the total conservation of energy for that is 1/2 mv escape. Ooh, I didn't mean to square the escape. V escape squared minus g times the mass of the planet times the mass of the individual particle divided by r, like this. All that's being equal to 0. If you want to solve for V escape, you get V escape is equal to, notice the common factor of its mass cancels out, and you get 2gm over r, where it's the radius of the planet, and you got to take the square root, so that's the radius of planet / moon. So that's actually what the escape velocity is. So if you take the mass of the planet, you take the mass of the planet or the mass of the moon and multiply that by the gravitational constant by 2, and then divide it by the radius of the planet and take the square root, that'll give you the escape velocity. And what I told you is, at least in planetary science, they sort of use as a rule of thumb that if it's 1/6 of the escape velocity, it will eventually escape. For instance, our Earth had a primeval atmosphere that had a lot of hydrogen and helium, believe it or not. But that hydrogen and helium, both of those are way too light, because hydrogen has a mass, even though it occurs as H2 instead of just plain H in the atmosphere of the Earth, that hydrogen has a mass of 2. Now, that's 2U, of course, but it's only 2 compared to 32 or 48, or excuse me, 32 or 28 like we did here. And helium has a mass of about 4. So again, that's 4 compared to 32 or 28. So both of those are way, way, way lighter. That's why we don't find much hydrogen or helium in our atmosphere. We definitely find way more in outer space in some sense. Any questions on that? All right, so that's a really big deal. What I wanted to do is I want to talk to you a little bit about this conceptual example. Well, I've got a more realistic viewpoint that I'd like to add, though this is correct. So let me go ahead, and I'm going to stop sharing my screen from my iPad. I'm going to start sharing my screen from my book. So let me see if I can find it. Yep, there it is. So this conceptual example right here is pretty good. It says a tank of helium is used to fill balloons. As each balloon is filled, the number of helium atoms remaining in the tank decreases. How does this affect the root mean square speed of the molecules remaining in the tank? So now notice the root mean square speed is really just 3 kT over m, where m is the mass of the molecule. So it's not changing the individual masses of the molecules. It's just changing the total mass of the molecules inside. So initially you should believe that, since the temperature, or since the root mean square velocity only depends on the mass, the temperature, and of course the Boltzmann constant, which isn't going to change, then there shouldn't be any change here, because you're just letting out atoms. That's sort of right, okay? Meaning if the actual tank remains the same temperature, and therefore the molecules remain the same temperature in some sense, then yes, the root mean square velocity is going to change. But I do know for a fact that when you connect one tank to another tank, for instance, in the case of scuba diving, and you fill up the one tank with the other tank, the tank that's being filled up gets hotter, and the tank that empties is getting cooler. So in principle, the temperature will actually go down, and since the temperature goes down, that would ultimately cause the tank root mean square velocities of the helium to actually go down. So I'll just add that extra little caveat of reality to it, because yes, if you take a tank and you release a lot of the pressure, which is what you're doing when you're letting some of the helium out, then you're actually decreasing the temperature because of Charles's law. Remember, it's Boyle's law is pressure and volume are inversely related. It's then Charles's law says that pressure and temperature are directly related. And then the Gay-Lussac law says that volume and temperature are related, if I'm remembering that correctly. As you can tell, I'm not going to ever ask you on a test which one's, well, Boyle's law I'm okay with remembering, but I'm still not going to ask you that because you guys didn't necessarily take scuba diving, which is Boyle's law supposed to be the scuba diver's law. But that being said, I'm definitely not going to ask you which one's Charles's law, which one's Gay-Lussac's law, which one's Dalton's law of partial pressures, which hopefully if I stated as just Dalton's laws, you wouldn't necessarily know, but you definitely would know it if it was Dalton's laws of partial pressure. But anyways, I'm not going to ask you that kind of question as which one's which, but it is perfectly reasonable at any point in this 242 course or any point in the 241 course, just about any point in the 241 course, to ask you what's Newton's first law of motion, what's Newton's second law of motion, what's Newton's third law of motion, what's Newton's law of gravity, what's Kepler's first law of planetary motion, Kepler's third law of planetary motion, Kepler's second law of planetary motion. All those are fair game once you've covered them in 241, even in 242. And when we get to the first law of thermodynamics, that's a fair question. When we get to the 0th law of thermodynamics, that's another fair question. When we get to the second law of thermodynamics, that's another fair question. So just keep that in mind. Us instructors think of those things as chucker questions, like really easy questions that everybody should know. And we put them on test often to give you, hey, here's some free points. But if you're not realizing that, hey, this thing that's called a law, maybe I should memorize that, then you're sort of in a bummer. All right. So now that I did that conceptual example, I want to show you another example. In this case, I'm going to show you an example of the difference between root mean square and just plain normal average. So I'm going to take some very specific numbers and I'm going to calculate the average, and I'm going to calculate the root mean square. And hopefully from that, you'll be able to see there is a significant difference, and you'll be able to understand what that difference is. And hopefully it'll let you know more about what the root mean square is. Now I clicked this, but it's still not sharing. Let's see. I'll try it again. Any day now. Any day now. It still shows a little wheel. Okay, fine, it's working now. So let's imagine the numbers x sub I, or actually let's go ahead and call them v's. Let's call the number v sub I, and one case is 1 meter per second, 2 meters per second, 3 meters per second. I'm going to ditch the units, by the way, so that's not going to continue. 4 meters per second, 5 meters per second, and in fact, 6 meters per second. And what I'd like to calculate is what is V bar and VRMS. So solution, V bar is defined to be V1 plus V2 plus ... over N, where N is the number. Well, I could actually do it by this saying Vn. So then you'd obviously see that N is the number of particles. And V root mean square is actually equal to the square root of the average of the squares of the velocities. So that would be V1 squared plus V2 squared plus ... plus Vn squared divided by N, and then take the square root. So let's calculate those two. So A, V bar is going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. Now 1 plus 2 is 3, plus 3 again is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. So that's 21 over 6. 6 goes into 21 18 times, or excuse me, 6 goes into 18 3 times. So that'd be 3. And then there's 3 left over, 19, 20, 21, and 3 over 6 is a half. So this would be 3.5 meters per second. Notice I left off the units when I was doing the calculation, but that's equal to V bar. So that's the average velocity. Now let's look at the root mean square velocity. So B, VRMS, is going to be equal to a square root. Now I'm going to say 1 squared is 1 plus 4, that's 2 squared, plus 9, that's 3 squared, plus 16, that's 4 squared, plus 25, that's 5 squared, plus 36, that's 6 squared. All that's going to be divided by 6. 1 plus 4 is 5, plus 9 is 14, plus 16 is 20, 30. And then 25 is 55, and then 36 is 80, 91. So this would be the square root of 91 divided by 6. Now 6 goes into 90. It goes into 60 10 times. It goes into 35 times. So that's 15 just to get to 90. So this would be the square root of 15.66, or excuse me, 15.555. Excuse me, 15.155. No, it's one. Yeah, I think it's either 16 2/3 or, yeah, it's 16 2/3. That's what it is. Let's fix that. So it's 15.16666, so on and so forth. It doesn't really matter too much. I'm going to take the square root of it. So I'm going to take the square root of 15.166. And that gives me 3.89 meters per second again. And that's V root mean square. So that's not too important of a calculation that you do day in and day out, but it's important for your understanding of the difference between root mean square and average. Okay. So does anybody have any questions on that? Your book does a problem similar to that as well. I think it's a good problem to think about and have you guys do. I'm going to go ahead and knock out the rest of the chapter now. It's 6:28. Class is supposed to run until 6:40. I got to tell myself that on occasion because I let my class out last night at 6:20 by mistake. So maybe y'all can help me keep up with that. That'd be cool. I wouldn't mind. But one thing you see from this expression is you see that the average kinetic energy. So this example is finished, but what we saw is the average kinetic energy was equal to 3/2 kT. And 3/2 kT suggests that as t approaches 0, the kinetic energy will in fact go to 0. And that's not actually true. We don't see that classically. So for instance, what I just derived was using Newton's laws of motion, which is classical physics. What we have discovered, at least at the microscopic level and the quantum mechanical world, that there's actually a 0-point energy, which is exactly the weapon that the villain on The Incredibles used. So the villain on The Incredible used a 0-point energy laser or beam or something like that. And what was discovered is if you one way you can do it is you can just model the actual atom, or you could say atoms next to each other, or in this case, I'm going to say the nucleus with an electron outside of its shells, which in the case of hydrogen is really only one electron. But if you just think of any element that has one valence electron, for instance, you could actually treat that like it's a mass, namely the electron, tethered to another central object, the nucleus, by a spring. And when you calculate that with quantum mechanics, what you find is that there's always a 1/2 h bar omega, or 1/2 hf, which is h is Planck's constant and f is the frequency, whereas h bar is Planck's constant divided by 2 pi, and omega is 2 pi times the frequency. So you'd see the 2 pi's cancel out. Anyways, that 1/2 h bar omega is the 0 point energy that we know they have. So even if you go down to 0 Kelvin, and there's a version of the second law of thermodynamics that says you can't make it there, but even if you did, the energy would not be zero. The atoms and molecules would still be moving. And one of the ways you can picture that is as a result of the Heisenberg uncertainty principle. Okay, so that's what I'd want to say about this. It does not imply, it does imply from that equation that temperature being zero has kinetic energy being zero, but I'm just telling you that the facts are that is not what happens. Okay, your book talks about that a little bit. Now, what I will tell you is that James Clerk Maxwell, who is the father of electricity and magnetism in some way, but to be honest with you, it's really, I've been reading a lot of biographies lately, and Michael Faraday was not unlike Oliver Heaviside, who Oliver Heaviside came after Maxwell, and in fact found Maxwell's equations beautiful and enlightening and very helpful. But both Oliver Heaviside and Michael Faraday were fairly quote unquote uneducated people, not unlike Ben Franklin. They were just sort of what Thomas Jefferson might have called natural aristocrats, like Hamilton would be, even though he didn't necessarily care for Hamilton. But these people were just naturally brilliant. So, for instance, Oliver Heaviside scored like second or third, very high amongst everybody that took a test that was basically your test to say whether you're going to college or not and how good you are on maths and stuff like that. And he took it at like, something the equivalent of 6th grade and did really, really fantastically. Michael Faraday never took such a test, as far as we know, but we know that his math skills were not that good. But he sort of single-handedly worked up through the ranks after finding a self-help book, kind of weird, but that in the this is even the early 1800s, late 1700s, found a self-help book in which it told him to, try to do things that he wouldn't otherwise do, like learn a new language or perfect your ability to write or stuff like that. And he took an interest in chemistry and read some discussions on chemistry, and then managed to hook up with a guy that was running around Europe doing chemical displays. And he learned a lot from him, and then went on to continue experiments assisting that guy, and then ultimately taking over for that guy. And he ultimately became the head of the Royal Society and did so many wonderful experiments, wrote down so many principles, just basically kept this wonderful notebooks full of all of his experimental thoughts and all of his experimental results, that Maxwell, when he came in as an occasion professor of mathematics at Cambridge, he said, I mostly just had to translate Faraday's writing into mathematics, and then I had the equations. Now, what Maxwell did was he found one inconsistency that technologically Faraday hadn't quite reached yet. So he might have, if technology would have been a little bit better, but he did find a lot of things in which he made up the technology. So we can't say that he wouldn't have, but either way, Michael Faraday provided the vast majority of the information to Maxwell's equations so that Maxwell could write them. And then Maxwell added a term to one of them that made them internally consistent and produced or made basically electromagnetic radiation possible. So this guy, Maxwell, he died in 1879. So this probably would have been around the 1860s, 1850s. He took the time to model atoms and molecules, which, by the way, we're talking again like 1850, 1860. The existence of the atom wasn't proven until 1905 by Einstein's Brownian motion paper. So this is a really big deal. But he, using statistical mechanics, imagined the properties of atoms and molecules. And from that, using statistical mechanics, was able to reach the conclusion that the number of molecules as a function of V basically gave the number of molecules that had a velocity between V and V plus dV given by, here's the expression. This is called the Maxwell-Boltzmann distribution, or the Maxwell distribution. It's 4 pi n times parentheses m, the mass of the molecule, divided by 2 pi kt, Boltzmann constant again, t. That's all raised to the 3/2 power. And then v squared, the velocity squared, and then e to the negative mv squared. Notice that looks like kinetic energy, and in fact on the bottom you're going to have a 2, so it's 1/2 mv squared over kt. That's the actual expression, and in fact the probability, or excuse me, the number of molecules with speeds between v and v plus dv is f of v dv, which equals, of course, 4 pi n m over 2 pi kt to the 3/2 times v squared e to the negative mv squared over 2kt dv. Okay, so that's a very big result. And in fact, you can see with that dv next to it, it's probably thinking, oh crap, I've got to consider taking an integral of that. And that's true. Okay, so this is the actual distribution of speeds. It's really wonderful. And in fact, there's even a graph of it in your book. Let me stop for a second and show you that graph. So I'm going to stop sharing here. We only got about 3 minutes left. And I'm going to start sharing right here. And that's the actual graph. Notice the graph has basically a speed 0, has essentially 0 particles at that speed, but it rapidly increases, reaches some max, and then slowly decreases. That's the way the function behaves. This VP is the most probable velocity. This V bar is the typical average. And this VRMS is the one we just worked with, which turns out to be the square root of 3kt over m. Now, can anybody guess, given that I told you this is the V that's most probable, and looking at this graph, can anybody tell me how you might go about getting that VP? Uh-oh, I've got my chat window closed to see. Looks like someone might have said something. See ya, Haley. Anybody? Okay. Well, it is the most probable. And if you look at it, it appears to be hitting the maxima. So the trick is taking the derivative and setting it equal to 0. If you take the derivative of f of v and set it equal to 0, you will get the actual most probable velocity. The good news is that you really don't have to do very much. You don't have to do very much to take the derivative, because the stuff that can become 0 is not the e, and it's not all those factors out in front. So let me quickly share screen. I've only got 1 minute. I'm going to quickly show you the derivative. The other part of this example down here on the next page is you integrating it to calculate the average velocity. I want you to do that and this derivative part for extra credit. This actually has it all worked out, but I need you to fill in the steps that it left off. So you either need to use the technique of integration called integration by parts, integral of udv equals uv minus integral of vdu, or use the integral table with the proper substitutions and compute this. I'm going to actually show you the derivative really quickly. So d by dv of 4 pi n m over 2 pi kt to the 3/2 of v squared e to the blah, 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 like that. I'm going to take the derivative of all that and set it equal to 0. Notice this junk right here can't make it 0. And in fact, that e also can't make it 0 because there's no exponent you can put on e to make it 0. So all I really got to do is take the derivative of this product right here. So I'm going to say 4 pi.
Professor?
Yes.
You're still sharing the textbook.
Oh, thank you. Appreciate that. That would be helpful. Okay, let me quickly do this. Thanks. It'll be on the notes eventually, but still, that's pretty slack of me. I think I heard somebody try to interrupt me a second ago, too. I wish I would have paid attention then. All right, I'm trying. It looks like it's trying to do it. Come on now. Come on. Crap, 1 minute late. Anybody needs to go ahead. I'm going to go ahead and do this on the video. So if you guys need to go ahead and split. I will also wait for the last person in case they have questions. I know someone wrote me a message. They had a question. You can also contact me after lab by email, and I'll pay attention to it. But anyways, when I go to take this derivative, all this junk is just going to come out front, and I'm just going to take the derivative of what's left using the product rule. So the derivative of v squared is 2v. And then I have the other part of the product is already there, blah, blah, blah. Don't really matter too much. Now it's the product rule, so I'm going to add it. And now I'm going to take v squared, but now I've got to take the derivative of the exponential. And the derivative of an exponential is just the exponential times the derivative of the exponent. So I'm going to get the exponential again, but right now I'm going to take the derivative of the exponent. So the derivative of the exponent is, you see it's negative mv squared over 2kt. I'm going to take the derivative of that. That's going to make it negative mv. The 2 would come down from the derivative, but that's going to cancel the 2 in the bottom. So it's negative mv kt, and then times e to the negative dot, 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 like that. All that being equal to 0 means basically all this stuff and the e to the negative dot, 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 those are just factors that can't be 0. And I have 2v minus mv cubed over kt is equal to 0. That's basically it. Notice you can cancel out one of the v's, and then ultimately what you get is v is equal to 2kt over m square root, and that's v probable. And that's it. So you guys are free to go. Again, you can turn this work in doing the integral to calculate v, the average velocity. So the only difference being you take this integrand, this whole function that you see right here that I'm taking the derivative of, and you multiply it by v, and then dv, and then integrate that from 0 to infinity, and that integration of this function with a v cubed instead of a v squared ultimately gives you the average v. If you wanted to know the square, the average of the square of the velocity, you'd multiply it by v squared. But in this case, you only multiply it by v because you want the average. So feel free to stick around, ask me any questions. Good luck in your lab. You guys might really want to consider going to Virginia Beach and getting one of the instructors or one of the maintenance people or one of the housekeeping people to let you in your physics lab, and you can actually take your class there on those computers. We won't be able to see you because they don't have cameras, or you could use your own laptop. That would work as well. But at least you would be right in the right place. So have a good one, everybody.
Oh, I just had a question too. I sent you the email too if you want to read it.
Okay, gotcha.
Yeah. Thank you.
No problem. Have a good one, Angelica.
You too.
Have a good weekend, Professor Younger.
You too. Thank you. I'm going to make some announcements on this video so y'all will see it when you watch it. But basically, the rest of the chapter, we're essentially done. It talks a little bit about van der Waals equation. It talks about the Clausius version of van der Waals equation. It does talk about partial pressures over liquids. So I would remind you that in the ideal gas law, if you're collecting a gas over water, for instance, there's going to be water vapor in there, and that's going to have a partial pressure given by the table in your book. I expect you to be able to do that stuff in your homeworks to some extent. I don't expect really hard ones, so the homeworks aren't very hard ones. So I do expect you to be able to use van der Waals equation and Clausius's equation and take into account the vapor pressure over water when using the ideal gas law. All of that's really great for homework, but I'm not going to test you on any of that. To be honest with you, from this chapter, what you really need to know how to do is calculate root mean square velocity, calculate average velocity by the integral of that f of v dv times v, and integrate or take the derivative of f of v to find the most probable velocity, be able to calculate, like I said, the root mean square velocities or the average kinetic energy, know what that stuff means, and use the ideal gas law. That's really what's important out of this chapter for me. Also, they do the mean free path in this chapter as well. That's also fair games for your homework, but I'm not going to require you to test on that material. The phase changes, all that stuff is stuff you should read. But again, I'm not going to ask you questions about that. I'm not going to ask you questions about evaporation. Relative humidity is another one. I think you should actually be able to do that on the test as well as in the homework. You'll see there's one example in there, and it shouldn't be any harder than that, where you just look up on the table and find out what the saturation vapor pressure is. And then the relative humidity is the partial pressure divided by the saturation vapor pressure. So that helps you. Boiling, changing states, all those things are good physical phenomena. They're the concepts you're supposed to know. Again, I doubt I'll ask you much of them except for maybe concept questions. But temperature decrease with altitude, that again is fun for homework, but not something I'm going to test you on. Van der Waals is not something I'm going to test you on. And like I said, when we get to the mean free path, homework's certainly acceptable. I love that little derivation. I think you should see if you can come up with it as well. That's a great thing. But again, I'm not going to question you on that on a test. Okay. Gavin, are you still here, bud?
Yeah, I was just listening.
Okay. No problem. I just wanted to make sure.
Yeah. All right.
Do you have any questions?
No, I was just staying for the class.
No problem.
All right. Have a good one.
All right. Have a good one. Take care.